Welcome back to the Explainer. So, have you ever wondered how the internet actually manages massive digital traffic jams to keep your video streams buffer-free? Today, we're exploring quality of service, or QoS, and uncovering the hidden mechanisms that act as the ultimate traffic cops of the internet.
We've all experienced this incredibly relatable frustration. You're on an important voice call, and suddenly you sound like a robot, or the call just drops completely. Yet at that exact same moment, a massive file downloading in the background on your computer finishes perfectly without a single hitch. Why does the network literally favor a background download over your live, real-time conversation? Okay, let's dive into this to understand the root cause of the problem and the ingenious ways engineers have tried to fix it.
Here is our roadmap for today. We're going to cover the traffic jam problem, identifying traffic, controlling flow, who goes next, IntServ versus DiffServ, and finally, why both architectures struggled.
Let's start with Section 1, the traffic jam problem.
You know, the internet was originally designed around what's called best effort service, meaning all packets of data just compete equally for bandwidth. Picture the internet as this massive, chaotic highway with absolutely no lanes, no speed limits, and zero right-of-way rules. A giant lumbering truck hauling a massive file download has the exact same priority as a tiny urgent ambulance carrying your voice call. When bursty data traffic meets real-time applications on this lawless highway, crashes and congestion are pretty much inevitable. The solution to all of this? Quality of service.
So to put a formal definition on it, quality of service, or QoS, is the set of mechanisms that reconcile these competing demands. It basically guarantees real-time delivery for specific, sensitive applications while simultaneously offering high throughput for everything else. Think of it as the ultimate system of traffic cops, toll booths, and VIP lanes needed to clear up our digital traffic jam.
Section 2, identifying traffic, also known as packet classification. Now, network traffic isn't all the same. It generally falls into three distinct profiles that demand unique treatment. First, interactive traffic, like your casual web browsing. It relies on small amounts of data, but needs a snappy, timely response. Second, file transfers. These guys pump huge chunks of data whenever they feel like it and remain idle the rest of the time, causing sudden, bursty waves of congestion. And third, real-time traffic, like video and audio. This stuff requires a strict minimum throughput and a hard cap on latency to work properly. And actually, those bursty file transfers, they are far and away the biggest threat to your smooth VoIP calls.
And this brilliantly illustrates how the network actually tells these packets apart. Down at the link layer, a network frame contains very specific fields, like the tag control. When a packet hits a network core, routers aren't just taking a wild guess at what's inside. They're reading these specific fields and tags to classify the incoming traffic. The router sees the tag, assigns the packet to the correct service class, and boom! It ensures that our metaphorical ambulance gets recognized immediately.
Moving on to Section 3, controlling flow, shaping and policing.
So we have two main ways to control the flow here. Traffic shaping tries to make the traffic pattern predictable. It actually delays packets to smooth out sudden bursts, acting literally like a leaky bucket. If you pour water in way too fast, it holds the excess and lets it leak out at a steady, controlled drip. Traffic policing, on the other hand, is a lot more ruthless. It acts like a strict speed limit. If packets exceed their allocated rate, meaning they go out of profile, the network doesn't politely ask them to wait. It just drops them entirely, or at best, marks them down.
To enforce these rules, engineers rely on mathematical models like the Leaky Bucket and the Token Bucket algorithms, and they operate based on two key parameters, the average long-term rate and the maximum instantaneous burst size. This is a really clever setup because it allows a customer to send a quick, harmless burst of data, but it completely prevents them from overwhelming the network with sustained, heavy traffic.
Let's trace how this logic actually operates in practice. When a packet arrives, the token bucket algorithm calculates the residual tokens. If the bucket has enough tokens, meaning the sender hasn't blown past their limit, the packet is allowed to pass, and those tokens are subtracted. But if not, the system takes action, perhaps forcing the packet right back into the queue to wait for its next opportunity. It's a highly efficient, entirely automated gatekeeper.
Section 4, who goes next? Packet scheduling.
Now, what's really interesting about this is the queuing discipline, or qdisc. It features completely separate enqueue and dequeue processes. A scheduler sits right between the input and the output. It doesn't just use a lazy first-in, first-out line where everyone just waits their turn. Instead, it actively dictates the transmission order, managing buffers internally and intelligently selecting exactly which packet gets to move into the transmission pipe based on incredibly strict rules.
And one of the most ingenious ways advanced schedulers pull this off is by calculating a virtual finish timestamp, or VFT. In systems like weighted fair queuing, every single arriving packet gets handed this value based on its size and its reserved bandwidth. The scheduler then just looks at the options and simply picks the packet with the smallest VFT to send out next. It's a brilliant mathematical trick because it ensures that a tiny, super high priority voice packet gets a tiny timestamp, allowing it to instantly jump the line right past those massive, low priority file chunks.
Section 5. IntServ versus DiffServ. Okay, this is the ultimate showdown between two massive architectural philosophies. On one side, IntServ tried to give everyone a private VIP escort. Its focus was per flow, requiring high setup overhead using the RSVP protocol to reserve a path all the way from end to end. It offered strict bandwidth and worst-case delay guarantees, which made it stateful, incredibly expensive, and wildly complex. DiffServ took a totally different approach. It focused on per-class treatment, practically grouping traffic into fast and slow lanes using tags, with no advanced setup required. Instead of strict guarantees, it offered expedited treatment, making it semi-stateful, highly scalable, and much easier for service providers to actually deploy.
Let's move to the Ingress stage and see how this builds when a packet actually enters a DiffServ domain. First, it hits the classifier. Then it slides over to the meter, where it gets measured against its agreed-upon profile. It gets categorized as either in profile or out of profile. Finally, the marker tags it accordingly, maybe remarking that out-of-profile traffic as just best effort or dropping it entirely, before forwarding the conforming traffic. It is quite literally a streamlined, scalable assembly line for traffic management.
Which brings us to our final section, Section 6, why both architectures struggled.
Back during the massive QoS hype in the early 2000s, the internet was booming. Multimedia was taking over everything, and researchers were frantically trying to implement IntServ and DiffServ to basically prevent the network from collapsing. But here's the crazy part. Despite all of this intricate architecture and genuinely brilliant engineering, neither IntServ nor DiffServ actually took over the global wired internet in the way engineers envisioned.
So the crucial point is the plot twist, over-provisioning. See, while software engineers were busy writing complex scheduling algorithms, hardware engineers made massive, game-changing breakthroughs in optical technology. Fiber optics made bandwidth so incredibly cheap and abundant that internet service providers basically just decided to build a 100-lane highway. And when you have a 100-lane highway, you don't really need complex traffic cops or VIP lanes anymore. The sheer volume of available bandwidth just solved the congestion problem on wired networks through pure brute force.
Now, I want to clarify that QoS is definitely not dead. It simply moved to where it was needed most. Today, QoS absolutely thrives in service-level agreements for enterprise VoIP, where businesses are actually paying for guaranteed phone call quality. It's actively working away right now inside your home end-user devices and local routers. But most importantly, it has found a permanent home out on the edge in wireless networks, like Wi-Fi and WiMAX. Out there, radio spectrum is still remarkably scarce, bandwidth is definitely limited, and active traffic management remains absolutely critical. Which leaves us with this final, really provocative thought. We live in a world entirely dominated by mobile devices and wireless connections now. As wireless networks become the new bottleneck for our frankly insatiable data demands, will the old QoS traffic cops make a full comeback? Will these intricate scheduling and policing algorithms ultimately dictate the future of your mobile data? It is a fascinating question to chew on the next time a video buffer is on your phone. Thank you so much for joining me on this explainer, and keep exploring.